Okay, welcome to that seminar today, and the speaker today is Logan Koo. So Logan graduated recently from University of Pennsylvania, and since then he has been a research assistant professor in our department. Logan works on algebraic combinatorics, and today he's going to talk about the Tutte symmetric function. So Logan, the stage is yours.
Thank you very much, and thank you all for being here, for organizing this. So I figured what better to talk about at the Tutte Colloquium than the Tutte symmetric function, one of the things that's been coming out of my research with Sophie. So we're going to be working with graphs, so let's go through what exactly a graph is for a minute. So a graph consists of two sets, a set of vertices, which are typically drawn as points on a plane, and a set of vertex pairs, edges, which are usually drawn between two of the vertices. So this is going to be our running example of a graph that we're going to be working with throughout. This graph is a graph of cities in the United States where I've connected an edge between them if they are connected by a flight with respect to a certain airline. I call this graph delta. And this is going to be how I'm going to refer to this graph. And, oh yes, by the way, if anyone has any questions during the talk, feel free to either unmute and chime in or post it in the chat. Either way is fine. And one thing I'm going to be working with is deletion and contraction of edges to represent things in the graph. So if I take this edge here between Minneapolis and San Antonio, well, very simply, if I delete the edge, then I get this graph down here on the left where this edge is simply removed from the edge set. And this is often denoted with a backslash or sometimes with a minus here. Alternatively, I can contract the edge. So I take the two endpoints and I smush them together into one hybrid city like San Francisco from Big Hero 6. In this case, it's Min Antonio. And all of the other edges that were in play stay and they get contracted. And in particular, Atlanta, for example, had two edges to the new vertex, one to Minneapolis and one to San Antonio. Unless we say otherwise, we just keep both of these edges in the graph. Our graphs can have multiple edges and they might have loops. And this contraction is represented with the typical quotient. And the Tutte polynomial and the chromatic polynomial, as they originally were, have to do with graph colorings. So a coloring of a map is assigning a positive integer to each vertex, and an in-coloring assigns one of the integers between 1 and n. And we call it coloring in part because this was originally brought up through maps also. You wanted to color every region in a planar map so that two different territories that bordered got different colors so the map's more readable. And this blossomed into this in part. And colors are usually represented by actual colors in graphs. So on the left here is a proper 3 coloring of this graph using blue, red, and green. And there is no edge that connects any two vertices that got the same color. Over here on the right is an improper 3 coloring because there is an edge at which the two endpoints got the same color. So building into where we go into Tutte's work, we start with the chromatic polynomial, which was first introduced in, I believe, the 20s by Birkhoff and popularized by then. So we define a function, a polynomial in one variable, chi g of n. We're going to let that denote the number of proper in-colorings of g. It is far from obvious at a glance that this is in fact a polynomial function. One way we can show this is by the famous edge deletion contraction relation, first described by Foster. If we take any edge in the graph and we want to look at chi g, we can break it into pieces by first taking chi of g, delete the edge, and evaluating that polynomial, and subtracting off the portion with g, contract the edge. So in this way, we can evaluate the chromatic polynomial inductively on a graph by deleting and contracting every edge and creating an expression. And for example, we can use this to show that chi g of n is always in fact a polynomial. If we have a graph with no edges, the number of ways to give it in colors is the number of vertices to the nth power. We make a choice, it's into the number of vertices. We make n choices for each vertex. And then as long as we have an edge, we can apply deletion contraction and use induction to show that every corresponding thing then is a difference of polynomials. And here's a visualization of this that I think will help make it easy to see what's going on. So I've rearranged the equation down here so that it's chi of g delete e is chi g plus chi g contract e. The reason that this counts proper in colorings and splits them appropriately is because we can split the cases for chi g delete e into two cases. Up here is a proper 3 coloring in which the endpoints of this non-edge in this graph got different colors. This corresponds to this proper coloring here, which is just the same coloring but with the edge in play. That gives us a proper 3 coloring of chi g, and it doesn't correspond to anything on g contract e. And on the other hand, if we have a proper 3 coloring of this where these got the same color, then we can contract them and give this same color to the contracted vertex here. It's easy to see this is still going to be a proper coloring in the contracted graph. It's still going to use 3 colors, and it's not going to correspond to a coloring over here. It's easy to show that this is a bijection. And that establishes this formula for any n. So Tutte was the next person to introduce something a bit further in the line of general polynomials here. He wanted to study, in addition, the connectedness of graphs. So a graph is called connected if you can walk between any 2 vertices along a set path of edges. And even if a graph's not connected, it has a number of different connected components, each different piece where you can walk between all the vertices in one component. There's kind of 2 fundamental and opposite kinds of edges that help describe this. On the one hand, we have a loop, which is any edge whose endpoints are the same vertex. A loop is completely redundant in terms of connectivity. We can delete it, it can be there or not, and it doesn't tell us anything whatsoever about how connected the graph is. A loop also comes about if you have a cycle and you contract all the edges but one, the remaining one's going to go to a loop. So somehow this loop is illustrating, that comes out of that illustrates the fact that the cycle has one too many edges necessary for it to all be connected. On the other hand, the opposite is a bridge, which is an edge whose removal will disconnect its component. In this particular graph, that red edge is the only bridge. Every other edge could be removed without disconnecting it, but not that one. So it's the opposite. You have to have it, and removing it completely changes the connectivity. So Tutte defined his diachromatic polynomial, or now called Tutte polynomial, and there's a number of ways you can define it that have been done by many people, but one way is for this recursive relation. So this is a recursive relation, kind of analogous to how you could do a recursive relation on chi g by starting with an empty graph and building up. So if g has only bridges and loops, then it gets x to the number of bridges, y to the number of loops. If it has any other edge in play that's not that, then we add the 2, g delete e and g contract e on x, y. One reason the Tutte polynomial is so nice and so well studied is that every polynomial function on graphs that's, I don't think I wrote here, multiplicative on connected components, which makes sense because for most functions you would do connected components independently. And if it has a deletion contraction relation that's linear, then it has to be a specialization of the Tutte polynomial. And there was a lot of work that gone into showing various forms of this universality of the Tutte polynomial, or a recipe theorem. Tutte showed some portion of it, Brailovsky showed some. There are a lot of people who contributed pieces to what exactly that means. And this includes things like the chromatic polynomial, and if you know of the flow polynomial, and a handful of other things. So here are some of the things the Tutte polynomial can tell you. It does specialize the chromatic polynomial through an appropriate substitution and a slight sign and change here. If you orient each edge of the, if you give an orientation to each edge of the graph, a direction it goes, then one evaluation of this tells you how many of them are acyclic, have no way you can go in a cycle following the directions. On the other hand, a different one, in fact, the mirror evaluation tells you the number of strongly connected orientations, one in which you can get from, I believe that's from any vertex to any other. And the number of spanning subgraphs, which is the number of ways you can take a subset of the edges to reach all vertices. That is adjacent to all vertices. and the number of forests, which is the number of sets of edges that don't induce a cycle. These are just some of the many things that the Tutte polynomial does. So in my research with Sophie, I study the chromatic symmetric function and the Tutte symmetric function, which goes a step further than this and looks at a function that's symmetric in a countable number of variables. It may not be obvious why we want to do this, because frankly, I can understand that at a glance that seems utterly bizarre. I will go into that a little bit as we go, but let's start right now with just the definition that Stanley first gave. Xg, a capital X to denote that it's somehow more general than chi-g. We use the countable number x1, x2 of variables, but instead of counting every proper coloring kappa with just, we count it and say it's an in-coloring, we do more than that. We take each vertex and we give it a monomial, an x term, corresponding to its color. So if I have a coloring kappa, and I have 3 vertices that get the color 1, then I get an x1 cubed here. If I also have 2 vertices that get the color 2, I get an x2 squared. And I'll give an example of this on the next slide to illustrate. So it tells you not just how many colors you use, but how many times you use each one. Now, this function is symmetric because if you permute the indices, you're still going to get the same function. Why is this true? Because if you take a proper coloring of a graph and you permute it, it's still a proper coloring. So if I have one monomial coming out of this, that corresponded to one proper coloring. Its permutation is still going to be a proper coloring that's going to give that same monomial, but with that symmetric permutation of the variables. And note that this is indeed properly a generalization, because what happens if I plug in the first in variables to be 1s here? Then what happens is that if kappa is a coloring that only uses the colors 1 through n, it gets counted once. So there's going to be chi-g of n of those. And if it uses a color bigger than that, then this term goes to 0. So that substitution gives us chi-g. And here's an example of how to compute x delta so that we can illustrate exactly what's happening here. So here's one proper 3 coloring of delta. And let's say that blue is 1, green is 2, and red is 3. So from this particular choice of proper coloring, we're going to get a term x1 cubed, x2, x3. And from this choice over here, there's 2 blue vertices, and there's 2 green ones. And so we're going to get an x1 squared, x2 squared, x3. So again, to illustrate, these are counted the same by the chromatic polynomial. They're both proper 3 colorings, and it doesn't distinguish them. But the chromatic symmetric function does distinguish them by telling us that it splits the 5 vertices differently. In this case, it splits it into a group of 3, a group of 1, and a group of 1 as stable sets of vertices with no edges in common, given by this coloring. Whereas this monomial tells us this one actually does it into a group of 2, a group of 2, and a group of 1. So that's one upside of using this symmetric function thing, is now we get some more information, and we get it visualized in this somewhat natural way here. And we want to make a Tutte version of the symmetric function. Now, from the version of the Tutte polynomial I gave earlier, it is not obvious how to symmetrize that. That was a polynomial in x and y, which didn't really have the same way to split something into partitions and give it variables. What Stanley did was he found an alternative version of the Tutte polynomial that does look more like this, and turned it into a symmetric function. So he created what we call xb. We call it xb because it's also called the bad coloring symmetric function, and tg was, well, already taken by, the Tutte polynomial. And this has an extra variable t in addition to our variables x1, etc. And what does this t do? We're still summing over colorings, but all colorings, not proper ones necessarily, every coloring kappa. We still take this monomial that we get out of the partition, the x sub i's to the number of the vertices that get that color, but we also get a factor of 1 plus t for every edge that connects to vertices of the same color. That's what the t is counting, as how bad the coloring is, how far away from being proper. And first of all, you can recover xg from this easily by setting t equal to -1. Then all of these terms are going to go away, except for the ones where this 1 plus t didn't actually occur in the first place, where there were no monochromatic edges. And if you do the same trick as with xg and you plug in this xb with n1s, the sum you end up getting is a sum over all not necessarily proper n-colorings of 1 plus t to the number of monochromatic edges, and it is a known that this carries the same information as the Tutte polynomial, and there is in fact a substitution of variables that takes t and n to x and y, and vice versa. I'm not going to go into that right now because it's not a particularly pretty formula, nor is it insightful, but this is that alternate formulation of the Tutte polynomial we use to create this symmetric function. So again, to illustrate an example, we still get the proper colorings. We still get this x1 cubed, x2, x3. That's coming out of this graph on the left. That's a proper coloring. But now we have lots of other colorings. Here's one that's a really bad coloring. We have lots of things that are blue, lots of edges that are giving us problems. So there's 4 blue vertices and 1 green. So we get an x1 to the 4th and an x2. But we also count there's 3 edges that connect vertices of the same color. And so we get this bonus 1 plus 2 cubed term. That's telling us how bad this coloring is. Now, again, as I mentioned, I'm going to get more into why these are interesting and what applications these have. But first of all, I do want to point out one thing. One of the nice things I highlighted was that chi-g and the Tutte polynomial have a deletion contraction relation. And in fact, that was one of the nicest things about the Tutte polynomial, is it represents kind of every nice thing with deletion and contraction. But xg and xb of g, although they're more general, don't really admit this. Why is that the case? Because every term has a total x degree that's equal to the number of vertices. So for every edge, xg and xg delete e have v of g total degree, but the contraction has 1 less vertex. Those monomials have total degree v of g minus 1. So there's not really any nice way you can correct for that, especially when there's infinitely many variables here. Even if you try to add in some factor that makes this work, it really just doesn't end up working nicely. And you have the same basic problem with xb of g. So these functions are nice in that they give you more information on these partitions, but at the cost of this relation. That's something that Sophie and I wanted to fix. It felt like it should have a deletion contraction relation. There's really no reason it shouldn't. And how we went about it is we introduced a vertex weight function. We give each vertex a positive integer weight. So on xg, we now have a new function which we call xgw. This is how we define our vertex weighted graphs. And now for each color, we count not the number of vertices that get that color, but the total weight of vertices that gets that color. For each vertex, if it's colored 2, it contributes an x2 once for every amount of its weight. So if x2 to the 5th is occurring in our term, that means that the color 2 is possibly assigned to 5 vertices of weight 1, or 1 vertex of weight 5, or 2 vertices of weight 2 and 1 of weight 1. Now it's telling us this total weight. And the same thing, of course, with xb. We just replace each instance of x kappa v with x kappa v to the weight. And why does this help here? Well, because now these functions are homogeneous of degree equal to the total weight of the graph. And that is a number we can arrange to keep constant through contraction. And how do we do that? When we contract an edge, we also contract the weight function in the sense that we add the weights at the endpoints. And when we do this, the total weight doesn't change. And the deletion contraction relation we end up with for xb is going to be this one. Notice how it's very similar to the previous one. We're going to get xb on g delete e, plus we bring in this t times xb of g contract e. Now we have this really nice relationship. And for the chromatic symmetric function we get from t equals minus 1, we get this thing. Note that this is actually exactly the chromatic polynomials relation. It's the exact same relation, we just fundamentally had to add these weights in to make it happen. So why is this true? For xg, the proof is exactly the same, basically. I do the same thing as before. So here, these vertices are colored, but they also have weights. So the colors represent the, well, color. And the integers next to them represent the weight of the vertex. So if I take a monomial from G delete E, so again, I've rearranged this formula so that everything's positive. If I take a coloring, a proper one, that gives these two vertices different colors, then this is going to give me a monomial. In this case, we're going to have x1 to the 5th, x2 cubed, because there's this green 3, and x3. And this whole thing's going to have the same monomial, because it has the same vertices with the same weights, and the coloring is still proper because adding the edge is fine. Coming down here, what happens to the colorings that give those endpoints the same color? Well, when we contract them, we add the thing. So in this one, we have an x2 to the 5th in our monomial. And here we keep the same color and we still get an x2 to the 5th. That's the part that we needed to make this deletion contraction relation work. And so this proof is really just the same as for the chromatic polynomial. It basically can take a lot of these kinds of proofs on the chromatic polynomial and just raise them with the deletion contraction relation to the symmetric function setting. And I briefly want to illustrate how it works on XB. It's a little trickier in XB. So first of all, notice I did switch these graphs because this is the way that the deletion contraction relation is positive. So I can keep everything as counting in a simple way. So up here now there's an edge. And now there's no edge here. So I'm going to do the same thing. So let's take this particular coloring. Again, doesn't need to be proper. It could be or not for XB. And if this doesn't have an edge, well, if these two endpoints get different colors, then I can take the same coloring and the monomial is going to be the same up to the 1 plus t. The main point we need to look for is how many edges are there that connect vertices of the same color. Here there's 3. And here there's also going to be 3 because this edge wasn't between two vertices of the same color. So this exact same coloring here is going to give us the same term. That's not going to be true when we take this edge and it connected two things of the same color, but so we do have to check a little bit here how this works. So one thing I want to go back to here, this didn't correspond to a coloring here because this vertex can't get a color that corresponds correctly. On the other hand, we can absolutely do this here. We no longer care about the coloring being proper. So this coloring works on all 3 graphs when both of those vertices get the same color. So what we need to check is that the monomials work out. So the top graph gets a monomial of, we have blue to the 7th, x1 to the 7th, and 1 of each other, x2, x3. And we're getting a 1 plus t squared because there's these 2 edges that connect vertices of the same color. Coming down to with the edge deleted, this has the same monomial, but 1 less 1 plus t because this edge is missing, it was deleted. Coming over here, we also have 1 less 1 plus t because this edge that was here got contracted. But we have 1 plus t, and then we get 1 plus t. That 1 plus t factors in and gives us that 1 plus t squared as we wanted. So this is the formulation that gives this the nice deletion contraction relation, and it's easy to go through and check that all of this is in fact bijective in a proper way. Does anyone have any questions so far? This seems a good point to take a second and see if anyone has anything they want to ask. Okay. So to briefly summarize what we've talked about here, and I'm going to write a little bit on this slide to summarize. So chi-g was the first function, and this was first described by Birkhoff in around the 1920s or 1910s, I'm not remembering off the top of my head right now. And this was used to describe maps of the plane. This was the original impetus for considering the chromatic polynomial, was coloring maps and considering some other things related to that. The Tutte polynomial generalizes chi-g, which is what I mean when I look at this. Arrow here, I'm saying that this is generalized by this. This is just a diagram containing this information. So this is the Tutte polynomial, which was created by and popularized by Tutte in, there were a handful of things in the late 40s and 50s where it really got popularized and then took off. Then we have Stanley, Richard Stanley in the 90s, generalized this here. He made xb and xb of g, which generalize these functions respectively and contain them properly. And why did he do this? I'll make a brief point here, which I'm going to get to in a second, but There's a reason that symmetric functions are closely related to symmetric group representations. Stanley wanted to study immanents, which are character formulas that generalize determinants and permanents. And there's a natural way in which symmetric functions correspond to these. I'll mention a bit more about that in a second. And over here on the right, now we've given these functions weights to incorporate this back the deletion contraction relations that we got from these that were lost in these. So just a brief summary of where we're at. The part I wanted to mention is that, so symmetric functions form a basis, let's say a C basis, although you can do it over any field, basically, that's of characteristic 0, and all of this is going to work fine. And how would we get a basis for symmetric functions? One way we can do this is we remember that we get nice things corresponding to partitions. Those two partitions we got before with delta, the x1 cubed, x2, x3, and the x1 squared, x2 squared, x3 were different. And in fact, they're independent of each other in a very natural sense. One basis of symmetric functions is taken by summing this monomial corresponding to a partition. And so a partition here is a multi-set of positive integers. So in this case, we define this monomial symmetric function corresponding to 3, 2, 2, 1 to be, we can view it as the chromatic symmetric function of this graph. So what do we get when we sum this graph? Each of these vertices needs to get a different color. So it's going to be a sum over distinct colors. And the one that gets put here is going to get weight 3. The ones that get put here and here are going to get weights 2. And the one that gets put here is going to get a weight 1. So basically we're summing, possibly with a slight multiplicity here, over all monomials of the form x1 cubed, x2 squared, x3 squared, x4, but permuted. We're going to get every monomial that has that exponent profile. The exponents are 3, 2, 2, and 1 for distinct choices of those variables. It's not hard to convince yourself that this spans the space of symmetric functions. You can always take any symmetric function and break it down into its pieces by the total degree and then by how many vertices get that. And it's not too hard to consider why it kind of has to be linearly independent. I'm not going to go into that right now, but these functions do form a basis. And in fact, the space of symmetric functions does also split as a graded algebra, a graded vector space. So these, as it ranges over partitions of, say, 8, 3 plus 2 plus 2 plus 1, is going to form a finite basis for that finite dimensional space. I'll talk a brief bit here about why this is related to symmetric group representations. If you remember from algebra, or if you work with this, characters of the symmetric group and the irreducible representations of the symmetric group are also indexed by partitions in a natural way. And in fact, there is a natural way to map many of these bases of symmetric functions on a partition, like 3, 2, 2, 1, to the character function that corresponds to 3, 2, 2, 1 as a character of an irreducible representation of Sn. So this is one reason that people like looking at things with symmetric functions. It has a connection to Sn modules. And in particular, when we look at symmetric functions that are always non-negative with respect to certain bases, that tends to say that those are in fact properly characters of Sn modules, because any character is a non-negative linear combination of the irreducible ones. So this is how we form these bases. Another basis is the graph complement here. Graph complement meaning anywhere there was an edge. I now put not an edge. So let's just take these vertices completely separate, 3, 2, 2, 1. Then I can color these independently. The first one, whatever I give it, if I give it x1, it gets an x1 cubed. If I give it x2, it gets an x2 cubed. And I get that sum independently, and then I can multiply it by the ones corresponding to the other things, because the chromatic symmetric function multiplies across components, because the colorings are independent. So this function is called the power sum symmetric function, because these are the sums of powers. And it's denoted by a P3221. Two other bases that are important that come up are this basis of elementary symmetric functions. We take E321 to correspond to the chromatic symmetric function of a disjoint union of cliques, graphs with this number of vertices with all edges in play. So E321 corresponds to this triangle, or three-clique, drawn in this way to make the drawing of the other one easier, times that of this two-clique times that of this point, and it's going to have this chromatic symmetric function. We get all sums of products of three distinct variables, because this has to be colored with three different colors, times two different colors times one different color. The other basis we wanted to talk about is the R basis, and this was popularized by a work of Peneguaio's recently, where he used this basis to figure out what the kernel of the symmetric function is. He proved exactly, if you view the symmetric function as a mapping from formal linear combinations of graphs into symmetric functions, you can prove that the kernel of that function is generated by a certain set of relations. And how he proved that is by reducing to this particular basis. And what is this basis? It's the complement of this one. Whereas here we took cliques of different sizes, that is, individual separate pieces that all have the same number of, that all had all edges in between them. Here we take it so that the only non-edges are those. So these three vertices have no edges between them. And these two vertices have no edges between them. And then there's this vertex over here, but every other edge in the graph is present. It's a multipartite graph, complete multipartite. This does not have a nice formula immediately, as the other ones do. So I'm not going to go into that. And why am I talking about these different bases? Because whereas with the chromatic polynomial, you can evaluate it at different points, or with the Tutte polynomial, you can evaluate it at different numbers. And that tells you something about how many acyclic orientations there are, things of that sort. You can do that with these symmetric functions also with these different bases. And what these different bases tell us gives us more information. So let's start with this M tilde basis. The corresponding property on Chi-G is this one. It's the number of colorings, which means one way you can view that is the number of ways to partition your graph into in-sets, and those sets have no edges inside of them, because a proper in-coloring does that. So that's the information you get from Chi-G. From XG, we get this extra information that we can tell what the sizes of the parts are. Like we mentioned, when we had two proper three colorings of delta, we can distinguish them because one of them induces parts of sizes 3, 1, and 1, and one of them induces parts of sizes 2, 2, and 1. And that ends up corresponding to the M basis. You can think about that because that's what we end up getting when we sum over these stable partitions. These partitions of the graph into stable sets. And in XGW, we now can tell the parts have given weights. In the Tutte polynomial, one thing you can do is we saw that you can figure out how to partition the graph into in pieces by giving them colorings, but we no longer require that the parts have no edges inside of them. In fact, we can tell how many total edges are inside of them because that was exactly what happened when we took this sum of 1 plus t to the e of kappa over all in colorings. These in colorings partitioned it into parts, and this number is the number of edges within parts because it's the number of edges connecting two vertices that got the same color. With xb of g, we saw that we can do this, but again, as with xg, we can tell what the sizes of the individual parts are. And with xbgw, we get the weights. With the p basis, what does this tell us? This gives us a state expansion where we can look at every subset of the edge set and figure out how connected the graph is when we look at only that edge set. So for the chromatic polynomial, if you apply deletion contraction to every edge, then this is the formula you're going to get. You're going to get this because when we delete and contract when we contract the edges in a specific subset S, we get this -1 to the cardinality of S from the deletion contraction relation. And what's left after you delete or contract every edge is a graph with no edges and only vertices. And how many vertices does it have? every connected component of the graph, when you use the edges in S, gets contracted into a single vertex. So you're going to get a term of n, the number of colors for chi-g of n, to the number of connected components. So that's where this sum comes from. It gives you some information about how connected the graph is when you take subsets of the edges. And analogously, you don't get this directly from tg of xy, but it's pretty clear how you get it from the corresponding bad coloring function from the previous slide. So now we don't get an alternating sum, but instead we get this t to the cardinality of s. So whereas these can have some terms cancel when you have s's with the same number, with edges with the same number of parity, so you can lose some information there. You don't lose that information here. If you apply the same deletion contraction proof to the chromatic symmetric function, remember that this p function, p sub n1 up through n something, was the same thing, the chromatic symmetric function, when we had distinct vertices with no edges. And it's the same deal. When we apply the deletion contraction to every edge, what ends up being left is there's going to be this component maybe with total, well, it's going to have 3 vertices, and you can prove it using the weight function and by using the proof on this, but it's still valid on xg, and in fact it was proved by Stanley without having to know the deletion contraction of the weight function, of course. So here you get, instead of just the number of connected components, you get their sizes. And the same here, but with t, and over here now we get the weights, and in particular what the weight function allows us to do here is give that nice deletion contraction proof, whereas you didn't have a nice deletion contraction proof of this fact here. The E basis is a weird one. So an orientation, as we mentioned, is when you assign a direction to each edge. And we call an orientation acyclic if it doesn't induce any directed cycles. This is a famous result of Stanley's, that the number of acyclic orientations up to a sign is chi-g of -1, which is funky. You wouldn't expect that this chi-g, which comes from defining it on positive integers, has an interpretation at -1, but it does. And this is something that Stanley showed, is it has a nice interpretation on every negative integer. But in particular, chi-g of -1 just simply is this. Another thing that Stanley showed later with xg is that you can further break this down by how many acyclic orientations have a fixed number of sinks, meaning a vertex that has no incoming edges, or no outgoing edges, excuse me. So what this ends up being is in the E basis, you get the sum over all integer partitions with exactly k parts of the E coefficient corresponding to that. So for a graph with 5 vertices, you can tell how many acyclic orientations have 3 sinks by summing E311 and E221. The 2 partitions of 5 with exactly 3 parts. And then sum those coefficients. And Sophie and I figured out how to extend this to weight functions, but this part is weird, because if you have an acyclic orientation of a weighted graph, and you have a vertex that's a sink, and it's weighted, how much weight does it contribute? Is it 1 sink? If it's weight k, is it k sinks? It's not immediately clear what the answer to that question should be. I would have assumed that it should be k sinks if it's weight k, but that's not really how it ends up working. We end up getting an alternating sum, and we don't just count acyclic orientations, but we count ordered pairs of an acyclic orientation of the graph times a map, which gives us a non-empty subset of the set of integers 1 up through the weight. So when we pick a sink, we end up picking actually not all of its, with weight k, we end up picking not all of its k vertices, but actually a subset of them. Somehow we're picking a subset of the k mini vertices inside of there to actually be true sinks. And we get a sign out of that. So it's an alternating sum that reduces to this case. It's a weird thing, and I'm not going to go too much into that, but this is a really cool thing that comes out of adding the weights, is that we now have a deletion contraction formula for this, and E positivity in particular, when a symmetric function has non-negative E basis coefficients, is very well studied, in a lot of places in symmetric functions because those correspond to products of sign characters of Sn. And so functions coming from graphs that are always e positive means that there's something going on with representations there. There's a famous conjecture of Stanley's about certain kinds of graphs being e positive, which is one thing that is well studied right now. And coming down to this bottom row, there isn't currently a published result that really generalizes either of these things, although I will say Sophie and I think we've just discovered one that we are writing up in the next week or two. So I hope that these two things will be completed soon and we have a result for them. It is well known that the Tutte polynomial also counts the number of acyclic orientations with a 1 sync, but based on the results Sophie and I found, we don't think this is the correct version of this to put into this diagram. There's a different version of this that I think will end up fitting more nicely with this and this. So I put this in here for now because it is a known result, but I think this will change soon. And there's one other basis that we've studied, and this is the R basis, the one of complete multipartite graphs brought in by Penaguayo. To explain what this does, we define a partition of the vertex set into different classes to be called edge maximal if there's an edge between any two parts. So this is a partition of our graph delta into 3 parts represented by the colors. And notice that the red part is connected to the green part by an edge, and it's connected to the blue part by an edge, and the blue and green parts are connected by an edge. Basically what this means is that this represents a proper coloring, but we can't combine any color classes. If it were the case that there were 2 color classes that didn't have any edges in common, then we could combine them into a bigger class. So these are in some sense maximal partitions of the graph into stable partitions, let's say. Although it need not be the case that they're actually stable because the parts themselves can have edges inside of them. And for any set of partitions of the graph, of the vertex set of the graph, we say that its intersection has parts such that 2 vertices are in the same part if they're in the same part in all of the intersecting things. So here are 2 partitions of the graph here. These 2 vertices are in the same part in both of them, so they stay in the same part. And these 2 vertices are in the same part in both. This vertex, though, was in one part in one and one in the other, and it doesn't have any vertex that it's in the same part with in both, so it just gets to be on its own now in its own little class in the intersection of the 2. What we end up with from the R basis, and this is a different result of ours from a different paper that we published in the last couple of months, is that what the R basis tells us is intersections of these partitions. In the case of XB, what we get is we let this be the number of partitions of G into stable sets that are maximal. Then what we get is an alternating sum over the intersections of these maximal stable partitions. So this is some new information we get out of the chromatic symmetric function that, as far as we can tell, doesn't immediately correspond to anything on chi-G or T of G. I did some research and I could totally be missing something obvious. And I'm absolutely welcome if somebody knows of something that corresponds to this. But I haven't found anything this generalizes on chi-G, which is interesting. The fact that it tells you about intersections of certain kinds of partitions. On XB, we no longer require our partitions to be into stable sets, into sets of vertices with no edges inside, but for each J separately, we can actually do this intersection on every partition of the graph that's maximal and such that there's fewer than J edges, less than or equal to J edges within parts, and still do this alternating sum, inclusion, exclusion-y looking thing. And for this one, we don't have any clue what it should be on weights. We have some ideas based on how certain things extend into R's, but we don't have anything concrete yet. So this is a very new thing. Penaguayo's result on the R basis was just earlier this year. And this is the first time we've been able to find an explicit thing that it tells us about the graph. So this is kind of the gist of what I've been going for so far, is that this chromatic symmetric function and Tutte symmetric function tell us a lot about the graph. One other thing I wanted to mention that these functions tell us is something interesting about trees. It's fairly well known that every tree with k vertices has the same Tutte polynomial and same chromatic polynomial. It's going to be x to the k minus 1 because in a tree, which is a connected graph with no cycles, every edge is a bridge. So it's just x to the number of bridges. The Tutte polynomial and chromatic polynomial literally just don't distinguish trees at all, other than how many vertices they have. Nonetheless, the chromatic symmetric function, so far, we have found no examples of trees that it does not distinguish. This has been verified by computer for trees of up to 29 vertices. There have yet to be a case of 2 trees that have the same chromatic symmetric function. Stanley mentioned this as an aside in his original paper on the chromatic symmetric function, but it's since built up quite a bit of a following since it was kind of expected that this would be easy to resolve, and it's not been. And it's surprising that this is still open in some sense, and it seems extra surprising combined with the fact that it's so completely opposite of the fact that the corresponding polynomials tell us nothing about the tree. And it turns out xg is equivalent to xb of g, so the Tutte symmetric function actually tells us the same information as the chromatic one on trees. So we can use its properties to try to figure out if there's some way to actually show that these functions give us enough data about trees to distinguish them. That's part of why we like these basis expansions, is we're trying to build towards this to some extent. The more information we can figure out that these functions give, the more likely it is that maybe this conjecture is true. And on the other hand, if the conjecture is not true, then we need some way to figure out why graphs might have equal chromatic or Tutte symmetric function. And that's of interest in its own right anyway. Stanley in his original paper first showed that graphs are not distinguished by xg. The smallest counterexample has 5 vertices. And I can even draw that real quick. Those 2 graphs are this one and this one. And those 2 graphs have the same chromatic symmetric function, and if you went through, you could verify that for, say, the partition of the number 5 into 3, 2, that both of these graphs have the same number of ways to partition the vertex set into a stable set of size 3 and one of size 2. And that's true for every partition, and that's equivalent to its chromatic symmetric functions being equal. Notice they don't even have the same degree sequence. And this one on the left has a vertex of degree 4. And this one doesn't. Although xb of g does tell you the degree sequence. The next big result was when Oriana and Scott gave a modular relation. They showed in particular that if you have a graph with a triangle on it, that its chromatic symmetric function decomposes in this manner, as an inclusion-exclusion, where we fix one edge of the triangle and include-exclude on the others. And in fact, this has also been shown to generalize to an n-cycle. And by using this, this relation, they were able to construct infinitely many pairs of graphs with equal xg. And Sophie and I have continued building on this in a paper that's still ongoing. We were able to construct infinitely many chordal graphs, in particular infinitely many split graphs with the same. And more interestingly, I think we were able to find graphs with arbitrarily large girth, that is, graphs where the smallest cycle is arbitrarily large. Previously, all of the known counterexamples, as far as I was aware, had triangles in them. We didn't even have an example that showed for sure that triangle-free graphs were not distinguished by xg. We, in fact, give a construction for any size of minimum cycle, and they even agree on xb of g, not just xg. It's not really our original construction because we borrow the construction heavily from a paper of Brailovsky's, where he does the same thing with an equivalent function. And we fine-tuned that a little bit to make it work. So as it turns out, we can actually show that it doesn't tell us this. And this seems like it's a little bit of evidence starting to run against the tree conjecture, because, I mean, trees are the graphs with infinite girth, no cycles, and no finite girth is distinguishable, but obviously there's also still a big jump between any finite number and infinity. The next step that would seem to make sense is if we can find bipartite graphs that have the same xb, because trees are all bipartite. So that would be the next logical step is, can we get closer to showing if there are trees that are the same? The next step is going to bipartite, perhaps. And that's about all I wanted to talk about, is that the Tutte symmetric function and the chromatic symmetric function are cool, and they tell you a lot of good things. They really combine a lot of the research from the past 100 or so years on chromatic polynomial, Tutte polynomial, and these symmetric functions, and it puts it together into one nice place. And this talk has been based on a series of 3 papers that Sophie and I have written. And in particular, this second paper we are releasing a new version of shortly. And that's going to be joined with Jose Alist Prieto and Jose Zamora, who are going to add some more data about how to construct graphs with equal XB. And thank you for coming. And
Oh, thank you, Logan. So any questions for Logan? Maybe I'll start with one. So maybe I missed from the talk though. So is it possible to deduce the unweighted version? So Stanley's, no, the unweighted version, the polynomial.
oh, from the weighted versions.
Yeah, from this symmetric function. If you properly choosing the weight.
This is actually a problem I studied some, yes. If you have the vertex weighted version of a graph, can you figure out what the unweighted graph is? Is, I think, the closest analog to that. Is that what you're saying?
That's right, yeah.
I don't know exactly. I'm not sure the extent to which that goes backwards into that on this same exact graph. I did some research on this during my PhD program at Penn, where I conjectured that maybe if you have all of the functions for vertices of weights 1 and 2, then that gives you back the graph entirely. And I don't know exactly. I don't know if you can go back from the weights to not the weights. It's because the weights more are a manifestation of combining vertices from a bigger graph.
Mm-hmm.
So I don't know exactly.
I see. It's not also known like there exists some weighting that gives the unweighted version. I guess that's the same question.
So there is one way you can get the graph itself, right? If you weight the vertices with, say, powers of 2. If you give it weights 1, 2, 4, 8, 16, etc., then based on the coefficients, you can explicitly tell which of those vertices has to have an edge in it by, say, the p-basis, which tells you connectivity. And so if you look at the coefficients in the p-basis, there's going to be one with the empty set, which is going to give you each vertex separately. And then if you look at all the ones with one fewer part than that, it's going to be adding 2 of those powers of 2 together. And you can tell which 2, because that'll be the 2 numbers that aren't appearing and are replaced by their sum. So from that weighting, you can deduce exactly what the original graph was. So there's at least that example.
Okay, thank you. So is there any other questions? Well, if not, let's thank Logan again for the nice talk. So yeah, so now we will move on to the backgrounds. So by the way, how do you like the applause? Does it sound realistic, or it really sounds too overwhelming?
Sorry, what?
The applause sound that I just played, I kind of feel that I missed the feeling of people giving applauses right after the talk. So I just download some audio. But I don't know if you're sitting on the other side, does it sound too odd to?
No, that was nice. I appreciate that.
You should stop the recording, Jane.
Oh, right.
That's true, yes.
Yeah, I